Welcome. In this video we'll look at ballooning modes and derive a simple formula for how they limit the pressure of the plasma. We'll look into many tokamak kind of design configurations, but the simple picture is also applicable to other more general cases. So here we'll look at just a simple kind of approximate expressions, and then in a later video I'll go through a more detailed mathematical calculation. But hopefully this will give you some physical insight into how these modes work. So essentially what we're talking about is you have a tokamak like this with a cross section like so. So this is a toroidal configuration like this, and the magnetic field lines are spiraling around like this. So we have the field lines which say start here, they spiral around the machine this way. And as they spiral around the machine, they go from the outside to the inside. So if I follow this around here, so we'll kind of spiral on the inside. As it keeps going, it'll reappear over here, and then it will spiral around towards the outside again afterwards. And so as you go around, it will kind of spiral around here and follow this kind of pattern. So end up around here and then around here. Now, on the outside of the tokamak is a bad curvature region. So if we draw in the curvature of the field lines, these field lines are mainly curved this way in the toroidal direction. So the kappa, the curvature vector is inwards. Here, curvature vector is inwards too. But the pressure is highest in the core here, and so we have pressure gradient this way, and pressure gradient also that way. And so on the outside of the tokamak here, we have a bad curvature region, and on the inside we have a good curvature region. And so in some cases it's energetically favourable for these field lines on the outside to balloon outwards. And because these field lines here are being stabilised, if these field lines move outwards, it would be stabilising, it would take energy to do that. And so it becomes favourable for these field lines to basically stay still. And then the field lines just move over here, which means you have a bending of the field line. So the field line is not moving here, but it's moving over here, and so the field line is being twisted, being moved outwards. And this is ballooning. So it's ballooning on the bad curvature side, also called the outboard. So it's the outboard side, and then in the middle here is the inboard side. And so we can try and understand this by stretching out these field lines. So if we draw a single field line, this is B for example, we have the outside, say is here, so this is the outboard, and then here's the inside, inboard, and again the inboard over here. And so a field line is stretching, is moving outwards on the outside, but it's essentially tied over here. And so a field line which is moving up like that. And if I draw in here some lengths, you see it's much longer along the field line than this distance. This distance here I'm going to call L parallel, is the distance from the inside of the tokamak where the field line is not moving, along the field line around to the outside. And if there's a safety factor, so safety factor Q is the number of times a field line goes around this way for every one time it goes around here. And so we can say that L parallel is very approximately is basically half of Q. So we're going halfway around the torus from the inside to the outside. So we have Q over 2. So if Q is equal to 4, for example, then we would need to go around twice around the machine to go from the inside to the outside. And every time we go around the machine, the distance is roughly 2 pi times major radius. And so this distance is roughly 2 pi times major radius, whereas this r is that distance here. So that gives us a length along the field line. This displacement here is the radial displacement of the plasma, psi r. And so now we can work out essentially how much the field line has changed by, so the delta B over B. So we say that delta B in the perpendicular direction divided by B is roughly the ratio of these two. So it's roughly psi r divided by L parallel. And so this gives us a way of working out the perturbed magnetic field. And we can use this to work out whether this is energetically favourable or not by putting it into the delta W equation, so the energy principle. So we have that delta W is like half, and then we have the two terms we're going to look at here. There are obviously 5 terms in total we looked at. This is the integral over all the machine. So first we have delta W, delta B perpendicular, which is this term we're going to derive here. And the other term we're going to consider here is the curvature drive term. So we have a P dot perp, and then we have a kappa. So there are terms involving J parallel, there are terms involving compression. Here we're going to assume that the plasma is essentially incompressible, and we're just going to look at the balance between this field line bending and this drive. So we have here, if the plasma is going to move outwards, it's going to take energy to bend the field lines, but there may be a drop in potential energy because the pressure gradient and curvature. And so we can approximate this delta B perp by using that, and then we can make an approximation for what this term here looks like as well. So at the outboard midplane, so this is like the radial perturbation, and so this part here is basically like dp by dr times psi r. And here also kappa is like 1 over major radius, and because it's inwards there's a minus sign, and this is also like psi r. And so this whole thing here you end up with psi r squared, and 1 over major radius from the curvature and a pressure gradient from here. And then we can put in this calculation for delta B into there. And so we end up with the delta W, and now since dp by dr is negative, so pressure is dropping with radius, this whole thing is going to be negative and so unstable if this second term is large enough. And so we can assume that this is occurring in a very small region, and so we can just say that the plasma will be unstable, so if this second term is bigger than this term. And since this is negative, we put a minus sign in here to make this whole thing positive. So if that is larger than, and so now we just put in the formula for L parallel, which we've derived here is basically a Q pi times R. And so L parallel here and so we can write down, rearrange this to work out something in terms of the pressure, dp by dr, and the magnetic pressure. So here are b squared and a mu naught. And so now this gives a limit on the pressure gradient, which depends on this magnetic pressure and this geometrical factor here involving the safety factor and major radius. We can turn this into a global limit by saying that the average pressure gradient, so if you have a pressure P0, say on axis, so dp by dr, so minus is roughly the pressure on the axis, so divided by the minor radius of the plasma. And so this is the maximum pressure in the plasma, and this is the minor radius. Then we can rearrange this a little bit. We can just write that we can put, so P naught on the left, we can take this magnetic pressure, this is magnetic pressure here, we can take that on the left hand side. And that, if that is bigger than this 1 over pi squared Q squared R, with this factor of A appearing over here, then it's unstable. And so this gives us a limit on this beta, because this left-hand side is the ratio of the fluid pressure to the magnetic pressure, and this is the beta. So this beta term must be less than this A over. It says A is minor radius, R is major radius, and then Q is safety factor. And typical parameters. So if you put in a value of Q equals, say, 2 at the edge, so e.g. So Q equals 2, and an A over R of about a third, then we'll give you a beta of about 1%, which is probably fairly typical for a tokamak, so a couple of percent is maybe the maximum. But this gives us a ballpark figure of the maximum achievable beta from ballooning stability.